Thank you so much, everyone, for coming today. So it's my great honor to introduce Chuang today. Ike really has been one of the pioneers of quantum computing, both in theory and experiments. He was definitely doing quantum computing before it was cool when he did his PhD here at Stanford on the subject. And he continued to pioneer the development of NMR quantum computers, and also made fundamental contributions to theory, most recently in some of the most efficient Hamiltonian simulation algorithms by qubitization, and even a grand unification of quantum algorithms into this one framework that we'll be hearing about today. And it's also a special honor for me to introduce Ike, because 14 years ago, this fall, I took Ike's class on quantum computing. I was a young graduate student, so he's made marks on the new list here on. So without further ado, please take it away.
Thank you, Adam, for the kind introduction. And I have to say, we still use Adam's project paper from that class as a standard for everyone to follow. With his permission, he gave his permission. Wow, I'm really impressed by all of you being here. This has got to be the most excited and intense quantum crowd I've spoken to in a long time. I'm curious, how many of you are from physics? How many of you are from engineering? Wow, okay.
Don't forget about applied physics.
How about chemistry? Only maybe one or two. Don't be embarrassed. How about from computer science? Still a little short there. Okay. And other fields that I haven't mentioned. Anyone from the business school? Question. I don't know if this is being reported too much, but is there any use for a quantum computer today that's economically important?
This is being recorded.
That answers that question. Okay, so what I have to share with you today is a relatively short talk about a piece of almost philosophy, because today where we are is at the nominal 100th year anniversary of quantum mechanics. And it made me think back to the birth of this field and to wonder what might we be missing today. So I'd like to begin on thinking about what it means to say the word nature. What does it mean to ask when we understand something from the basic nature of its existence? And arguably, if we look back 100 years ago, there was a different. There it is.
Oh, I see.
If we look back about 100 years ago, the state of physics was asking these kinds of questions. Why does an atom not decay? Why doesn't the electron in an atom collapse and cause it to just explode? Because the atom is negative, the nucleus is positive. Why in the black body radiation of something that's warm and emitting light, isn't there an enormous amount of ultraviolet short wavelength radiation? Because that's what classical physics predicts. This is called the ultraviolet catastrophe. And in this came the realization that we did not understand nature. This is what nature was doing, and we did not have theory which explained the stability of atoms or the lack of the ultraviolet catastrophe. And into this world, about 100 years ago, came Heisenberg in 1925. And he entered this thinking with three interesting principles. These principles were, first, that one should look at the observations of something. This is arguably from Ernest Mach, a philosopher who said that science should look at what we observe and its relationships, and nothing else. So focus on observations of things. Second, that there should exist local and global tensions in whatever you're observing, and that this existence of local and global is fundamental to the nature of things. Plato said, what we see is not the real world, but a shadow of it. There exists something greater that you do not have access to, because there's something global in addition to what you get to see locally. And third, an idea, arguably from Immanuel Kant, that the order of observations has consequences. Kant said something like, our knowledge depends on how we inquire. And if you inquire in a different order of what you know or determine that you think you know, may be different than if you had inquired in a different order. So these ideas that base your thinking on observations, think about contextuality, and think about non-commutativity really form the basis of what Werner Heisenberg led as the theory of quantum. So maybe we could call this the nature of quantum from the standpoint of Werner Heisenberg, because what Heisenberg did was to take the observations from Niels Bohr and from Max Planck and combine them to think of their mechanical implementation. And he came up with this equation, which involves the observation forward as a matrix. He came up with this observation that if you look at the momentum uncertainty and the position uncertainty, and you multiply them, that product is lower bounded by some constant. And then the idea that order of these observations makes a difference. If you observe momentum before position versus the other way, then you get a different result. And these three pieces of what he called philosophy that led to nature led to quantum mechanics. Okay, so this is what I would like to call nature, and I would like to understand as being what we would like as a goal for a different area. In parallel to this work in physics, another thing was also happening at this time, about 100 years ago or 90 years ago. And that was the idea of algorithms. In the field of algorithms, it has been well known from a long time ago that multiplication, addition are easy in the sense that the number of elementary steps we need to do is proportional to the square of the number of digits in the input to this problem. And we'll call that easy in the sense that it's very different from another class of problems. In fact, this particular class was even looked at by Alan Turing in his unpublished notes of 1951. He asked, how hard is it to factor a number? So somebody tell me right away, what are the factors of 1703?
Well, let me get that back.
It's going to be ChatGPT racing against John Simon. So Simon, what is the answer? Okay, actually, I gave a version of this talk in front of a bunch of cryptographers, and everybody yelled out the answer to me. So.
13 and 131.
Yeah, 13 and 131. Okay, so I chose a funny number because this is a trick number, and those trick numbers with the 1 and the 3 and the palindrome there made this a special case that everyone had memorized such kinds of things. You know, so now that you have read,
You have weird friends. Right?
now that you have read Cryptonomicon. Okay. Anyway, think of this as a hard problem. And the interesting thing is that Alan Turing started to devise a mechanism to solve these kinds of problems, and you probably know what it is. It is a tape that is infinite in length with a head that can read and write local ranges on this tape. And here's a beautiful picture of a rendition of such a machine that somebody lovingly made on Wikipedia. And it is able to compute all of those problems. And in computer science, we think of there as being a fundamental divide, because according to the Turing thesis, or its strong version, which I give you here, any physical realizable model of computation, be it a mechanical machine like this, or some others that I'll show you in just a moment, can be efficiently simulated. That means that if it's doing some kind of computation that's polynomial, like addition, multiplication, it'll stay polynomial. If I'm doing something harder that might be factoring, it'll stay hard like that. And all of these can be reduced to a version of this tape and head machine with addition of some randomness. So the strong Turing thesis claims this. And in fact, something that was happening before Alan Turing's time was that people were making computation machines that were really purely mechanical. Some of you recognize this, probably Alan Babbage's machine. And this, Charles Babbage's machine. And this is a machine based on classical mechanics. It has gears representing zeros and ones. And by the way, I urge you not to forget this kind of history. Because even if we're making quantum computers, you really want to know where all these concepts came from. And this orientation appears representing zeros and ones. And in fact, the foreman of the effort who made this, Charles Babbage, was a professor of mathematics. He was like an atom along the tape. And then he came up with these crazy ideas of something to make, and somebody else had to make him. And the foreman of the effort who made these had to standardize how screws were made. So it is because of this effort to build a computer that today we have 420 and 832 screws. It's small. It's small. Yeah. Instead of M3, it's M5. But it's kind of interesting how many things come from such grand efforts. In this case, we start to realize that even this machine, it qualifies as a mechanical computer, and it could be an electronic computer or any otherwise. They still should be simulatable by this machine, assuming it's sufficiently large, and that largeness won't be all that much bigger than your current machine. So like this, whatever Apple M something laptop that Professor Simon is using should be simulatable by Charles Babbage, who's over here, with only a polynomial slowdown. On Windows and Mac OS as well. And that's really mind-boggling to realize, because a challenge came to this. Richard Feynman in 1985 threw down a gauntlet, which was to say, what if I changed one word and made it a quantum mechanical machine instead of a classical mechanical machine? Now, all of you know where this is going, and it's not a surprise that this question came about. And of course, in 1995 came Peter Shor's algorithm, Richard Feynman's simulation algorithm, and Love Grover's search algorithm, such that this thesis was falsified. We now know today that this strong Turing thesis is not true. It makes a difference whether you're quantum or classical, whether you can solve a certain class of problems in polynomial time or exponential time, apparently. And so I want to wonder in this talk why that's true, why there's the gap between quantum and classical, and conceptually where this gap comes from. So let us return to Werner Heisenberg. Imagine that Werner Heisenberg wasn't doing something in 1925, but rather something in 1995. A young Werner Heisenberg who had just seen Shor's algorithm, Grover's algorithm, and Feynman's simulation algorithm. Maybe he would have applied those three ideas of nature to them, namely the idea that operators define all descriptions, local and global operators exist in tension, and that the order of operators has consequences, but in the field of opposites instead of in atoms and blackbody radiation. If this had been the case, I think that he would have said that it's very natural to think of computation as operators. Maybe he would say, instead of y is a function of some input, he might say transform the functions, the Heisenberg picture of computation. And I think he would also agree that the notion that operation order makes a difference is perfectly reasonable. If you want to bake bread, you want to put the flour and not, first into the oven because you haven't made the dough yet. So the order of these is very natural to algorithms. But what would you do about local and global operators being in tension? Where do you ever think of local and global in the concept of computation? Do we think about that in our world of quantum computation? Well, let's spend a little bit of time on that. Because if you looked at some random textbook, you would get this idea that computation is very naturally irreversible. An AND gate loses information, and it's going to be irreversible and nonlinear in that sense. But that's perfectly fine for quantum computation. It's a seminal result that we can fix that, fix the fact that there's a tension here. Physics is reversible. It's a differential equation, Schrodinger's equation here, which can go backwards and forwards easily. And the way we resolve this irreversibility versus reversibility is with Charles Bennett's result, that we can take the computation and change it. We can make the computation reversible by just adding a little bit of extra space and a little bit of extra time, and the overhead is not large. Therefore, we're fine. Therefore, we actually can work in this thing called the church of the larger Hilbert space, and thus quantum can inherit everything from classical computation, and it seems like we are done. This is orthodox quantum computation, and if you haven't looked at this before, it's just a big assumption that we all use in the field. Is this the right assumption? Are these the right gods to be praying to and assuming in our religion of quantum computation? That is what I'm questioning now. In fact, it means, by the way, that Professor Simon's MacBook is just running one big permutation right now. Windows is a permutation operator.
Running Mac OS.
OS is also a big permutation. Does that even make sense?
Even Sequoia.
Even Sequoia, it's a thing. Okay, but let's think about this. Do you actually ever think about local versus global tensions in normal computation? Well, in fact, I claim that it really does not make sense to think of real world computation as being a big permutation. It does not make sense to utilize this church of the larger Hilbert space argument. In fact, if you go back to John von Neumann started with this very nice idea of there being a CPU and memory. This is kind of like Turing's tape. It's a large size memory with a CPU that has a small window into it. And every one of you who has ever tried thinking about programming a microprocessor, it has to do with realistic issues of fetching instructions and data and dealing with a cache memory, because you need balance locality and global distribution all the time. In addition, just like Professor Simon here, if any of you have ever relied in your life on like ChatGPT for something, which I think he does.
I actually just repeat it. It's running all the time. I just say what it tells me to say. It's telling me to say this right now.
Yeah. So this is Professor GPT over there.
Yes, I can definitely give you an answer.
Yes, just wait for it to think for a little bit. Then we'll realize, what makes LLMs possible? It is really one mechanism that came out in that paper about LLMs, known as the attention mechanism. Attention is all you need. What is the attention mechanism? It's a large dot product between a key value pair. By the way, for those of you who don't know, I've been teaching machine learning for the last 8 years now. So has been the largest class at MIT until recently. 800, 600 students a semester is what I was dealing with until recently, because I really wanted to understand this. So the attention mechanism is a global attention mechanism, a global way of paying attention to patterns that works in tension with the locality of the rest of the recurrent neural network that is going on. So somehow computation has at its heart a tension between local and global. Somehow, though, in our textbook understanding of quantum computation, we don't have that. So we need to get rid of this kind of a picture if we're going to be able to really use that tension properly. I claim that what we need to do is to start again with this irreversible computation picture and not change the assumptions of the computation, but instead force the physics to adopt to the irreversibility there. And I believe, and I'm guessing, that what we need to understand is how to understand and formalize the physical behavior of subsystems. Imagine that you have a function that's embedded with the larger system. The larger system is unitary. Let us act on the subsystem with some function, which is the one that was over here. Now we're going to have a tension between the local part that's operating F and the global that's left over in the rest of the system that is comprising of how you've embedded your function in the physical system. In this formulation or conceptualization, we now have a local versus global tension. Is this real? Will it actually truly describe what we're doing in quantum computation? Well, if we call this a Heisenberg picture of computation, let me share with you what Heisenberg might have done, might have invented. He might have said the computation is a transformation of data, so it's F going to G. We don't transform A to F, A to Y. We'll transform the functions, just like we're thinking about operations and what we observe. Next, it is clear that we need to think not of the function as being the entire system, but of something that is embedding the function with some, say, unitary operator. If we embed like this, another degree that we have, and we'll call this a block encoded operation, another degree of freedom that we'll naturally have is doing the global operation. And a lot of physics, a lot of computation is done by trading back and forth between the local and the global. So let's ask for just one thing for global. We have a phase shift if we're in this block, and we have a phase shift if we're in this block. Let us call that operator Z. And let there be an arbitrary phase that we can apply depending on whatever, whether we're in this block, we get an e to the IP, if we're in this block, we get an e to the minus IP. It's almost the simplest possible thing you could ask for as a global operation. One of the really remarkable things is that now if I alternate back and forth between this u sub x local and the z sub p global operation, the order of those operations clearly has consequence. In fact, can transform an f, which is embedded in the u sub x, to a different function g. And this consequence, it turns out, arises from a very, very simple piece of physics that came about in the art of nuclear magnetic resonance. So this is known as the idea of composite pulses. And let's start with the blocks here. So we'll have an x-axis here and a z-axis here. And if we think of these gates as being rotations about those two axes, the question we're asking is what in the world you can do, whether you can take this embedded here, the cosine of theta, that's just the rotation about the x-axis, and we'll ignore the other elements. And I'd like to transform this f to some other function like a g over here. And I'll only give you some operation that changes the phase between these two elements. That's a rotation about the z-axis. So you could go and build this on a little mechanical model of a sphere and see what you get. So here are the Pauli matrices, and let's interleave the x rotations with the z rotations, just like I showed you in the last slide. So we do a local operation, a global phase shift, a local and global. And people have done this for decades, 40 years or something, since the very start of Darien NMR and the Stanford Magnetic Resonance Laboratory, because experimentalists needed to compensate for crappy amplifiers in those old days. The amplifiers were too strong or too weak or changed with time. They wanted the functions to be independent of time. So originally, that's how they thought about this. But now I'm here to tell you that you can treat that differently. You can think of the function. It's easy to multiply these 2x2 matrices together and get the function, which will be a polynomial in cosine of theta. Very easy to do that. But now let's think of that as an actual computation, not as errors that you're trying to get rid of. So it's that MRI image that you're sharpening. That's now the input to your computation. And the kinds of polynomials you can get are clearly these kinds of top hats, which is well known, but also other functions like the cosine and sine. You can also get a step function, which delineates between left half and the right half. You can get something that looks like this, which is almost like an approximation of 1 over x, like if this is x. And then you can also get something that looks like e to the minus x. You can get all sorts of polynomial approximations of well-known algebraic functions. And these are all encoded inside whatever sequence of phases you put into these z rotations. So again, the input is this function. The output is a new function, just like a Heisenberg picture of computation. The amazing thing about this is not the fact that the polynomial is a product of these matrices like that, but rather that there's a, and that happens depending on some structural conditions, which are reasonable because this has to be a unitary matrix. The really remarkable thing is that it works in reverse. This is truly outstanding. You design, you can determine the polynomial you want, and there's an algorithm which will take that polynomial. If it has order d, it will produce a length d sequence of real values here, which will let you construct that polynomial, as long as it satisfies some reasonable structural conditions. And this polynomial can be found by a textbook algorithm in discrete time signal processing, like the Oppenheim-Schaefer textbook, called the Ramez exchange algorithm. So in other words, this is like a program that gives you a polynomial. And it's a program that would be implemented by a quantum mechanical operation that's going back and forth between local and global. The fact that this is possible is really remarkable. Of course, though, this input here is a simple function, and we've only looked at 2 by 2 matrices. So this function is really just a constant here. So it's a little bit trivial so far. However, it turns out that you can not just have a number turns into a polynomial of a number. It was realized that this idea, which is called quantum signal processing, also works on block encoded matrices. Imagine that you have a block matrix here. So this is a large matrix, it can be very large, million by a million. Doesn't even have to be square, it can be rectangular. It could be a million by 1,000. And it's in some block form. And suppose our goal is to transform this matrix to another one. Well, this matrix, whatever it is guaranteed to have a singular value decomposition. That is, I can rewrite this matrix as a product of a unitary, a diagonal, and a unitary. But these are called the singular left and right vector matrices. And this is a diagonal with positive, non-negative real values, both numbers, called the singular values. Geometrically, that is that any transform that skews and rotates can be broken up into a rotation, a shrinkage, and another rotation. And we all know this. How many of you use the singular value stuff? Not much in physics, it turns out. Singular values are sometimes used in quantity types, like for the Schmidt decomposition, but they're extraordinarily important in engineering. And this is how Netflix makes its recommendations for the videos that you're supposed to watch.
Well, then it's not very good.
That's called collaborative filtering. And the problem it's not so good is because you have to be close to the mean for it to work well. This gentleman is far too singular to singular value decomposition is really hard, though. It's an extraordinarily complex, its complexity is exponential in the log of the number of bits in the system. And what is neat is, though, that if you do a appropriate combination of local, global, where each one of these is one of those embedded matrices, then you can get a polynomial transformation of the singular values as a result. The real remarkable part about this is that you do not need to know the SVD to be able to transform the singular values this way. This was a really big surprise to me. This is a result now known as the singular value transformation. It's an algorithm invented by Andras Kilian, Yan Su, Guanghao Lo, and Nathan Wee. And I think it's the single most important quantum algorithm advance since Peter Shor's algorithm. And I'll say a few words about why I believe that to be true. And one caveat. So in order for this to be possible, you need one ingredient, which is the block encoding of this matrix. This is that local encoded in global idea. And it is not terribly natural to get the ability to control something on the global scale and also have ability to do your function on the local scale at the same time. Yes, sir.
Can I ask what I think is a really dumb question? I hope it's really dumb. Can you say a little more physically, like, I'm trying to, I'm supposed to think about this as representing the high dimensional Hilbert space of a set of qubits? Like what should I think of this matrix as being physically?
So Professor Simon has said, what should I think of this matrix as being physically? You should think about it as whatever the answer is ChatGPT would give to you.
Plants?
I'm sorry. Pausing to give time to my running ChatGPT over here. No, really, this is a hard question to ask, but there are some simple examples of it. So like a recurrent blockade interaction, I'm trying to use Simon speak as I answer this question. I don't know if I get it correct or not.
Are there any cavities in this?
Are there any cavities? There could be, yeah. So for example, if this is a recurrent atom array, then you have a blockade operation. The blockade is conditioned on some qubit like this. If the qubit is 0, then no blockade happens to this set of qubits. If it's 1, it does. So I drew this here because I'd like you to think of it as a control matrix operation. When this is 0, nothing happens. When this is 1, this big thing over here happens.
I see.
Yeah.
So in other words, I should not think of this as some Hilbert space thing, because there the information isn't encoded locally in any kind of a medium.
I never think of anything as a Hilbert space type thing. We should always think of it as like
In terms of locality and physics.
yeah, some renditions. So Professor Monica Schleyer set up, for example, might have this as being, instead of just all to all, is there being a shared cavity photon? Now I'm talking to him. A shared universal cavity photon conditioned upon which the bunch of atoms do some operation or not. Now, if I put that shared cavity photon into a superposition state, then we get a superposition of this A happening or not. The reason I draw it as a 2x2 here, a block of 2x2, is because I really want to capture this as conditioned on one qubit being 0. This is 0 and this is 1, then A happens. And if I have that structure available, that means I can do this A on, say, the atoms. I do this phase shift on that single global photon. I do this A, I phase shift on a single global photon. And that pattern of going back and forth between local and global gives me this.
Okay, I understand. So you're saying the way I should understand that matrix equation is this the system that's getting operated on and the control.
That's right. But there are quotes around this.
I understand. Yeah.
It's simplified in that sense that there may be better ways of realizing this. In fact, one of the grand challenges I would like you in the audience to think about is, does such a structure exist naturally somewhere so that we could take advantage of it and not have to build it artificially? Because you may have an array of superconducting qubits or atoms in some system where you already get some natural embedding of, hey, there's a block here and a way to control whether that happens or not. If you have this structure of local and global tension, and the ability to phase shift, whether you're in the block or outside of the block, you get this quantum singular value transformation. Why is that important and interesting? It's not just because this is a cool mathematical result. It turns out that you can really immediately see almost that sequence of flipping back between X and Z notations looks a lot like Grover's algorithm. So Grover's algorithm conceptually in this picture takes a constant here, and the polynomial U1 is a big step function that amplifies that C to value 1. So I've just described Grover's algorithm to you. It's an extremely simple instance of this quantum signal processing. But I've gone more. In fact, if you block encoded a Hamiltonian, so with 0, you get an H. With 1, so if you're over here, you don't get H, you get something else. And you've made this unitary in the right way. And then I choose the phases, the piece, give me a cosine and a sine, and add them up, I get e to the IHT. I get the time evolution. So I've suddenly got a Feynman simulation algorithm in one sentence based on this idea of singular value transformations. But there's more. I really sound like I'm selling you knives. This next one involves a slicing and dicing operation. So here we're going to cut Hilbert spaces. And the idea is if you embed a unitary which does modular experimentation in a operator like this, which is easy to construct, then make a step function that says, are you on the left-hand side or the right-hand side of the block sphere? You really literally are cutting. And you do a binary search on cutting, halves, quarters, eighths, and so forth. You get Peter-Shor's factoring algorithm. You get every single major quantum algorithm out of this one idea of local versus global tension. And this is really neat to me. But I really want to dwell on one more thing. Why might Heisenberg have like this? It turns out that this quantum signal processing idea has an uncertainty-like relation in it. Just like Heisenberg's delta x, delta t, if the degree of the polynomial goes up, that trades off between the sharpness of the decision that you can make, like this sharpness over here, written in the right ways. And the product of those two, the degree of the polynomial times the polynomial sharpness in the right units, is bounded below by a constant. That is, in order to make it sharper, you have to reduce the error, so it's 1 over sharpness. In order to reduce the error, you have to make the degree go up. This is well known from polynomials. Now, it governs an algorithm, behavior of how well you can make a quantum algorithm work. So I hope I've been able to share with you that there's an interesting new way to look at quantum algorithms. This new way has led to a whole range of new approaches that unify not just these three algorithms, but also quantum walks, numerical integration, gift sampling, Wolfson machines. My favorite is quantum computational sensing, which is a story for another day. But also that there's a story behind all of this. If we take nature to be somehow the combination of the three ideas of Werner Heisenberg, that operators define all descriptions, there must exist a local and global tension, and that the order of operations has consequences, then maybe Heisenberg might have come up with a story that algorithms can be understood, the nature of algorithms can be understood by mapping these to transformations of functions, a Heisenberg picture of computation, a tension between local and global, just like in the Turing machine, but now in a very simple quantum mechanical way, and that going back and forth between these local and global operations gives you some kind of algorithm that has an uncertainty-like behavior behind it. Therefore, maybe we can understand something about the relationship between this global and local. I've been astounded to understand recently that there's actually a nonlinear Fourier transform that relates these phase coefficients with this polynomial that's used over here. Go and ask Professor Ha about that, because he's one of the leading people understanding the nonlinear Fourier transform. It's like a Fourier transform, but with matrices instead. Now I really sound like I'm selling knives for next commercial. But this is an astounding story to me. Much of it is a great surprise. It's not just this universality notion, but the notion that maybe quantum signal processing and quantum singularity transforms are the quantum of algorithms. Thank you. I'm just calling people.
No.
Sure.
Good. So earlier in the talk, you talked about the fact that the Church-Turing thesis was proven wrong. But that proof didn't actually involve like the famous. It didn't involve Grover or Shor, right? It was about sampling. And I'm curious if the singular value transformation has sort of an explanation for that.
No, it does not. But it admits other scenarios which are quite interesting, such as communication complexity as well. So you can create exponential gaps in more than just the canonical strong Church-Turing thesis. Of course, the strong Church-Turing thesis also assumes the non-collapse of the polynomial hierarchy. So we can only go so far with that. In the back.
So in an actual physical setup, let's say in superconducting qubits, how would you, I think you might have explained it, but I didn't fully understand. How would you actually realize that global phase shift like this as the Z operator let's just say superconducting qubits. How would you actually do that?
Right. So you can imagine that if you're converting between a local and global basis, one way to do that would be to perform a Fourier transform. So you could do a local operation, Fourier transform all of your bases, then you have another local thing, and then Fourier transform back and iterate back and forth. It's almost exactly how you would do a numerical simulation of a Hamiltonian that has a potential term and a three-particle kinetic term. So that's a trivial way to say that it's possible. It's not at all efficient to do that. But you can imagine that you might encode one qubit and have a large complete gate array or schematic gate array or something so that you condition some operation like the Hamiltonian and turn it on or off. Or you might trodderize a Hamiltonian and then condition each one of the trotter terms on a control qubit. So all of those show it's possible to do this. The key is I don't know a really compelling, easy way to do it. And that's where physics and cleverness could come in. That's where Professor Simon could come in. Simon and Schuster.
Why am I today's whipping boy? Fields? What did I ever do to you?
Because you have that clever idea that's been distracting me all during my talk. It's like an amazing idea that I can't get rid of right now. Which might actually provide this thing, and we'll talk more about it.
Excellent talk. Does this framework give you a way of thinking about error correction?
Does this,
novel and efficient scheme?
Does this framework give you a way of thinking about novel and efficient schemes for error correction? The answer is possibly, because what the scheme does is give you a universal architecture. And it tells you where you might care about errors and where you might not care about errors. Did you all know that error correction and fault tolerance are a key concept behind why your Intel CPUs work so reliably? It turns out, and I only learned this from the architecture team at MIT, who played a major role in figuring out that there is a sensitivity analysis that has been done now to figure out which bits in your classical processors you're most sensitive to. And they made those line widths of those transistors involved larger so that they're more reliable. They came up with clever ways of doing this instead of talking down an enormous error correction code that every single bit had to run. Probably quantum computers want to do something similarly clever because error correction is too costly, too big, too unrealistic, and it's very unlikely that we'll be able to make such large quantum computers if we have to be useful. If we have to realize error correction at the scale that people currently think. This scheme, where you flip back and forth, well, here you don't care about Z errors in that global bit. Here you have the reverse of that. So now you know something more about the structure of what you want to protect. But more than that, I can't say more. It's still going to be hard.
Yeah, thanks for the nice talk. So I guess my understanding about signal processing was that it is a language for describing, any sort of quantum algorithm described as a polynomial framework, but that, it's not necessarily the case that an actual implementation of these algorithms, like an actual implementation of Shor's, is most efficient in like the quantum signal processing language. So is there a way to think about, you have this universal language, converting that to what we know are sort of more specialized ways of implementing these algorithms that are far more efficient? Is there a way for our understanding that conversion, which is important for actually thinking about using this for each context?
That's a fantastic question. When I was a PhD student here in the late 90s, one of my mentors was Von Pratt. And I asked something similar to Von Pratt about classical computers. It's like, should I build a Turing machine to build all of my network workstations? And he said, of course not. That's why I helped create Sun Microsystems. There's a much better and efficient way to do that. So that's what you should do. Go found the quantum stuff.
But like, I guess my question is not like, there are obviously more efficient implementations. I'm more wondering, like, what does framing everything in this universal language teach us about achieving those more efficient realizations? Like, it's nice to have a language, but what does it actually teach us about how to realize this?
Yeah, I'm sorry I gave you a glib answer to your previous serious question. So let me try to give you a better answer. I get a list of new algorithms that this has led to, and that's one idea. And the other one, which I'm really much more excited about than algorithms, is using this language for the task of sensing. Because, for example, I tried to use that in meeting Monica Schreier-Smith's students this morning, where I, in my mind, listened to the measurement protocol they were using and translated that in my mind to, there's a bit of sensing and there's a bit of quantum processing. That quantum processing actually can be explained in many cases as something iterating back and forth between local and global, because that's a very common pattern. And that iteration then lets me show how her protocol fits into a language which could be generalized. And therefore I can know what asymptotic performance behavior I might expect if I took her protocol and took it off to infinity and beyond. And you know, this is the power of languages. It gives you a connection to all other kinds of instances that utilize that language, so that we could see the universality of her cavity atom protocol fitting superconducting devices, fitting trapped ions, and so forth. So that's, I think, where it probably will go. And maybe that I can say more about that, but I hope that helps.
Yeah, thank you. I was wondering if for your computation where you work on a smaller subsystem, is it important to, can you make the distinction of that dynamics, whether it's like Markovian or non-Markovian?
So in the dynamics of this particular system, I think that one of the biggest open areas of subsystem physics is understanding noise and concepts like Markovianicity. And I don't think that we have the right language for that and the understanding of that in order to say, right now, these are block operators, one after another. In a real system, you might ask for the Hamiltonian of quantum signal processing or the Lindbladding of quantum signal processing and try to make it continuous time instead. And by the way, for those of you who are excited about machine learning, these coefficients phi can also be thought of as trainable parameters. And then maybe you'll turn this into a gradient flow exercise instead of the fixed time block version that I showed here. Then the concepts of how much Markovian or non-Markovian behavior you have would be relevant. But other than that, I don't have a good answer for you.
Thanks for the nice talk. So when we think about Turing machine, there's a halting condition, right? After finite steps that it halts. So when we think about this local global permutation, does it approximate, does it match any algorithm in a finite permutations, or does it get closer and closer to a certain algorithm as you make an infinite amount?
Right. I'll use that question as an excuse to advertise Lin's beautiful work on something called infinite QSP. So infinite QSP would be the class of languages accepted by a QSP machine in the limit that you do an infinite number of iterations, or made the time step of each one of these infinitesimally small. And it seems like the class of such infinite QSP things turns out to be intimately related to the nonlinear Fourier transform. And I find it fascinating that Lin points out that what NLFT is, in a sense, is a kind of matrix, polynomial version of matrices. What happens if you have matrices as your polynomial terms instead of scalars? And that idea has been invented and reinvented over and over in many different fields. So we don't yet know if there's going to be a halting problem-like thing, because that field, to my knowledge, is not really connected with computer science. This might be the first of those kinds of connections here, but absolutely the mathematics folks are very interested in that infinite limit.
Thanks for that nice talk, but I guess it's maybe somewhat naive as a question. So the way I'm looking at the quantum signal processing and quantum singular value transform, and maybe a naive idea is like, let's say your operator is like a really big like density matrix. So in a sense, can I interpret it as like an efficient way of simulating like nonlinear dynamics on like density matrix or like an arbitrary quantum state? in this case?
Yes. In fact, the neat thing is that normally you think of quantum theory as being highly linear. We say it's a linear theory by definition. It's only when you look at a subsystem that it becomes nonlinear. And this is just the first of, I think, what will happen as many examples of how to find nonlinear behavior in a linear system by looking at the right subsystem. But this is the only case I know of where we have so far of construction that goes in both directions. Very easy to multiply lots of behavior and take a subsystem and find that it's nonlinear, but it's very difficult to decide on a nonlinearity you want and then have ways of tuning it in efficiently to get exactly that nonlinearity. So go ahead and restate your question if you want it to be sharper.
Sorry, Ken. I guess like if I want to tune it slightly sharper, then like one thing I'm thinking is like, is it in a sense like we can say this, like we can efficiently simulate any nonlinear process on the matrix? Not really, because if that is the case, then like in a sense you can simulate any nonlinear PDE efficiently with quantum mechanics, which I find it a little bit doubtful.
Good. And the answer is I do not know, but I highly encourage you, if you're like from the physics community, to talk with Adam, your science community, because that's the new dialogue that needs to happen to understand how far this can get. That nonlinearity is almost an example of that last equation I showed you, where there's a E times delta type uncertainty relation that we know. But we don't know if that will govern every possible one of these embeddings or not. We don't actually know the cost of getting nonlinearities efficiently in an asymptotic regime out of whatever resources you're given in the linearly physical system.
So the circuit that you showed for doing this quantum signal processing involved you both being able to control A and control A dagger. Is there still an efficient way to do it if you don't have access to the inverse of the operation?
That has been addressed in the literature, and you can do that for under certain assumptions, but maybe not generically, because that A dagger is tantamount to having the inverse with reversal of time. And reversing time can often be costly.
One more question.
Oh, I was going to ask, is there interest in applying this nonlinearity, this idea of nonlinearity in the system to making neural networks? Since I know neural networks need nonlinearity to these activation functions. So is that a direction of interest in the field?
Is there interest in taking this to create nonlinearities, for example, for neural networks? And the answer is yes. And one of the most interesting examples I can cite for that is Hartmut, Nevin, and Eddie Parkey published a paper which did this flip back and forth between local and global. They were motivated by a quantum algorithm called QAOA, approximate optimization algorithm. But it has almost the exact structure as this, except that the fees were discovered by doing some gradient descent instead. So there's certainly interest in finding the connection, the appropriate connection between this kind of structure and things like neural networks and linear feedback shift registers and many other structures in computer science. And so let me end by advertising then. I highly recommend all of you physics folks go study finite state machines and take the introductory FSM class or the complete mathematics class that used to be taught by Donald Knuth. Because then all that new idea will open your mind to a completely new set of problems and ideas and constructions. And vice versa, I recommend that those of you doing computer science
Learn how to solder. Take my soldering course.
There you go. Learn how to solder. Also, just figure out the physical realizations of the abstract things that you're talking about. Because maybe you'll see a log encoded operation just pop up where a physicist might not have seen it before.